The examples in this video go with the lesson 11.1, Sequences and Series. Example 1, write the first four terms of the sequence defined by the nth term. Part A, b sub n is equal to 2n plus 3. Okay. For part A, all we're going to do is we're literally going to start plugging integers in, starting with 1 and going all the way through 4, because we're finding the first four terms. Okay, so b sub 1 is going to be equal to 2 times 1 plus 3. That's going to give me 5. B sub 2 is going to be equal to 2 times 2 plus 3. That's going to give me 7. B sub 3 is going to give me 2 times 3 plus 3. That's going to give me 9. And B sub 4 is going to give me 2 times 4 plus 3. And that's going to give me 11. So the first four terms for the sequence, where this is our pattern, are 5, 7, 9, and 11. All right, now for part B, we're going to do the same thing. The sequence is called D, so this is D sub n. This is equal to -1 to the power of n times n squared. All right, so our first term, D sub 1, this is going to be -1 to the first power times 1 to the second power. This is going to give me -1. D sub 2, this is going to be -1 to the second power times 2 to the second power. This is going to give me a +4. D sub 3, -1 to the third power times 3 to the second power. This will give me -9. And D sub 4, this is our fourth term, -1 to the fourth power times 4 to the second power will give me +16. So the first four terms in our D sequence are -1, +4, -9, and +16. Example 2, write the first 5 terms of the sequence defined by C sub 1 is equal to 5, C sub n is equal to 3 times C sub n minus 1 minus 4. So this sequence is defined what we call recursively. Now C1 has already been found. We want to find C sub 2, then that's going to be 3 times C sub 1 minus 4. In our case, this is going to be 3 times 5, because that's what we knew C sub 1 was, minus 4. This will give us 11. C sub 3 can be defined as 3 times C sub 2 minus 4. That means we'll have 3 times 11 minus 4, and that will give me 29. C sub 4 can be defined as 3 times C sub 3 minus 4. That gives us 3 times 29 minus 4, and that will give us 83. And C sub 5 can be defined as 3 times C sub 4 minus 4. In our case, that's going to be 3 times 83 minus 4, and that will give us 245. So the first 5 terms of our sequence, and we already said C1 was equal to 5, are 5, 11, 29, 83, and 245. Example 3, evaluate part A, 9 factorial divided by 2 factorial times 7 factorial. Okay, there's actually a shortcut here that we can do. Remember, 9 factorial is actually 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. But all of this right here, 7 times 6 times 5 times 4 times 3 times 2 times 1, is the same thing as 7 factorial. And why that's important is because I'm actually dividing out a 7 factorial down here. So what I can do is 2 factorial is actually 2 times 1, and I'm not even going to bother to expand that 7 factorial because I already know they're going to cancel. This 7 factorial will cancel with all of this right here, which is also equal to 7 factorial. So what I really have is 72 divided by 2, because 9 times 8 is 72 and 2 times 1 is 2. This fraction reduces, and it will give me 36. Part B, we have n minus 1 factorial divided by n factorial. Okay, n minus 1 factorial is going to be n minus 1 times n minus 2 times n minus 3. So we're continuously decreasing that one. But n factorial can be written as n times n minus 1 times n minus 2 times n minus 3, and so on. And this piece right here is actually the same thing as n minus 1 factorial. So what that tells me in my fraction is the numerator will cancel out with all of this stuff right here because it's equivalent to that, and it leaves me with an n. But the n is down here in the denominator, and it has to stay in the denominator. And since everything canceled out in the numerator, we have to leave a placeholder up there to keep that n down in the denominator. So this fraction actually reduces to 1 divided by n. Example 4, given the sequence defined by c sub n is equal to 2 to the power of n divided by n plus 1 factorial, find c sub 4. Well, basically, they're just asking us to find the 4th term in the sequence. And really, all we're going to do is we're going to take 4 and we're going to plug it into n and all my formula parts there. So c sub 4 will be equal to 2 to the 4th power divided by 4 plus 1 factorial. All right, in the calculator, 2 to the 4th is 16, and 4 plus 1 is 5. In the numerator, we have 16. In the denominator, we have 5 times 4 times 3 times 2 times 1. Now, we can actually multiply those together and then reduce the fractions, but if we're smart, we can take a little bit of a shortcut here. For example, I know that 4 can divide into 16, and it will leave me with 4. And I also know that 2 can divide into 4, and it will leave me with a 2. That leaves me with a 2 in the numerator, and in the denominator I have 5 times 3 times 1, which is 15. And I can get there a little bit quicker by doing it this way. This is just reducing as we're going. It's called cross-canceling. Example 5, find the nth term, a sub n, of a sequence whose first 4 terms are given. Part A, -5, +6, -7, +8. Okay, the first thing I notice here in part A is that our terms are alternating signs. We have a negative and then a positive and then a negative and then a positive. Well, one way that we can make that happen, and we saw this in an earlier example, is if we take -1 and raise it to our power of n. When n is odd, we're going to get a negative number. When n is even, we're going to get a positive number. All right. Then the next thing I notice is that I want to get the numbers 5, 6, 7, and 8. Well, one thing I can do is, if I know my first power is going to be 1, what is it I can do to 1 to get to 5? Well, I could add 4. Okay, so we know 1 plus 4 is going to give me 5. Well, my next term, my power is going to be a 2. Does the pattern still hold? If I add 4 to 2, will I get 6? Oh yeah, okay, so this might actually work. My next power is going to be a 3. If I add 4 to 3, am I going to get 7? Well, yes, I do. Okay, and then because we can actually make a pattern work for the first 3 sometimes, we do have to check the fourth one and make sure. So let's see, my fourth power is going to be a 4. If I add 4 to 4, I will get 8. So it looks like I'm going to take whatever my power was and add 4, and then multiply that by -1 to the n power, and that will give me, or that will generate the sequence that we have over here in part A. All right, for part B, let's see, let's look at what we have. On the top we have 1, 1 times 2, 1 times 2 times 3, 1 times 2 times 3 times 4. The next one's probably going to be 1 times 2 times 3 times 5. Now, this could be written as 1 factorial, 2 factorial, 3 factorial, 4 factorial, and so on. So it looks like the next one's actually going to be 5 factorial. So we're going to have n factorial. All right, in the denominator, my numbers go 3, 9, 27, 81. Okay, these are all powers of 3. This looks very familiar. So we have 3. 9 is the same thing as 3 to the second. 27 is the same thing as 3 to the third. And 81 is the same thing as 3 to the fourth. So there's a good chance that my next number is going to be 243, or 3 to the fifth power. So it looks like we're going to be dividing by 3 to the power of n, and that will give me the nth term for my sequence. Example 6, evaluate the sum. Part A, we want the sum from I equals 1 to 5 of the quantity 3i plus 1. Our first term is going to be 3 times 1 plus 1, and we want to add that to our second term, which is 3 times 2 plus 1, and we want to add that to the third term, which is 3 times 3 plus 1, and we want to add that to the fourth term, which is 3 times 4 plus 1, and then we want to add that to the fifth term, which is 3 times 5 plus 1, and we can stop there because it told me to stop when I got to 5. And so we're adding these 5 terms right here together, and we'll get the handy dandy calculator out, and this is going to give me 50. Part B, we have the sum starting with n equals 2 and going to 5 of -1 to the power n plus 1 times 1 over 2 to the power of n. All right, so we are going to be adding -1 to the power of 2 plus 1 times 1 over 2 to the power of 2 plus -1 to the power of 3 plus 1 times 1 over 2 to the power of 3 plus -1 to the power 4 plus 1 times 1 over 2 to the power 4 plus -1 to the power 5 plus 1 times 1 over 2 to the power of 5. And we can stop here because that's where it told me to stop. So I'm only adding 4 terms this time because I started at the second one instead of starting at the first one like I did for part A. All right, let's get out our calculators and see what we get. And this is telling me my sum here is -5 divided by 32. All right, part C, evaluate the sum. from 1 to 4 of 4, right? My first term, when k is equal to 1, is 4. There's nowhere to plug it into, so it's just a plain old 4. My second term is 4 again. Again, there's nowhere to plug it into. My third term is 4 again. My fourth term is 4, and my fifth term is also 4. And so 4 plus 4 plus 4 plus 4 plus 4 is going to give me 20, and that's my sum. Example 7, write each sum using summation notation. Part A, 2 factorial divided by 7 plus 3 factorial divided by 14 plus 4 factorial divided by 21 plus n plus 1 factorial divided by 7n. So basically, our formula has already been figured out for us right here. This is how we're going to generate these terms back here and everything in between. So when I do my summation notation, we want to have the sum of, we want to have n plus 1 factorial over 7n. Now, keep in mind, we want to generate this particular sequence right here, which has n's in it. And so I really want to stop here at n when I fill it into the formula. Now, what that means is that I'm actually going to have to go back and take these n's out of my formula here and replace them with a different variable, whatever variable you want. And I'm just going to throw an x in there because we usually use x, but really you can put anything in here you want to. Okay? And our starting point is going to be x is equal to 1 because 1 plus 1 is going to give me that 2, and 7 times 1 down here is going to give me that 7. So it looks like our summation notation right here it is. We have the sum of x plus 1 factorial over 7x from x equals 1 to n. Part B, we're going to have to actually figure out what that formula is because they didn't give it to us because we only have 4 terms. Now what that tells me is when I do my summation notation, I'm going to be stopping here at 4. And we'll be starting probably at 1, but not necessarily. Okay, things we notice over here. On the denominator, I notice that I have multiples of 5 here. Actually, this is 5 to the first. This one's 5 to the second. This is 5 to the third. This is 5 to the fourth. So it looks like I'm going to have a fraction, and the denominator is going to be 5 to the power of my variable. And I'm just going to put an x here because I used x the other time. And I'm going to start at x is equal to 1 because 5 to the first power is going to give me that 5. 5 to the second power is going to give me that 5 squared, and so on and so on. Okay, now we just have to figure out what's going to go on the top. We have 1, 8, 27, and 64. Now, actually, there is a pattern that's going on here. This one's a little bit difficult to tell about, but 8, I know is the same thing as 2 to the power of 3, and 27 is the same thing as 3 to the power of 3, and 64 is the same thing as 4 to the power of 3. So we could actually write 1 as 1 to the power of 3. So it looks like we're actually going to take our term, whichever one it is, and we're going to raise it to the third power. So 1 to the third power will give me 1. 2 to the third power will give me that 8. Then third term, 3 to the third power will give me 27. And I need to do one more thing to this. I'm almost finished. Notice that my terms are alternating. I'm going from a negative to a positive, back to a negative, back to a positive. So this is actually going to have to be multiplied by -1. And we should put a power on it. And we'll just do whatever power of the term that we're on. So for odd powers of x, we'll have negative terms, like the first term and the third term. And then for even powers of x, we'll have positive terms, like the second term here and the fourth term. So here is our summation rule to generate this series.